Okay, in this video, I'm going to talk about the Hardy-Weinberg equation and particularly what the different terms, the different variables are representing. Okay, let's get started with P. P in the Hardy-Weinberg equations is going to represent the frequency of, and I'm going to abbreviate, it's going to represent the frequency of the dominant allele. Q is going to represent the frequency of the recessive allele. And really, all of these terms are going to start off with frequency or percentages. So when we're working in the equations, we're going to work in decimals or in percentages. Okay, so together, P plus Q, our first Hardy-Weinberg equation, is going to equal 1. What this means is that the dominant allele, the percentage of the dominant alleles, plus the percentage of the recessive alleles are going to equal 1 or 100% of your alleles. That's because for any trait, the alleles are either going to be dominant or they're going to be recessive. My next three terms are not just strictly talking about one allele, but they're talking about allele combinations. For example, P squared is going to represent the frequency of, I'm going to abbreviate again, the homozygous dominant genotype. In other words, P squared is going to represent the percentage of my population that is, for example, big A, big A. Q squared, on the other hand, is going to represent the frequency of the population that is homozygous recessive genotype. So, for example, whatever percentage of the population is little a, that's going to be represented by Q squared. My last term, and think of this as one full term, 2PQ. Don't leave off the 2 whenever you're working with this term. 2PQ is going to represent the frequency of the heterozygous genotype. So these, once again, are genotypes or allele combinations, versus up here we were just strictly dealing with what percentage of the alleles are dominant versus recessive. My second Hardy-Weinberg equation is going to take these last three terms, put them together. So P squared plus 2PQ plus Q squared, once again, is going to equal 1. That's because in a population, individuals can either be homozygous dominant, heterozygous, or homozygous recessive, and all three of those categories will add up to 1 or 100% of your population. So when you're working with problems, one of the hardest things to do is to realize what term the problem is either describing or what term they're asking for. So think to yourself, are they talking about an allele combination? Or are they strictly talking about what percentage of your alleles are the dominant or big A allele versus recessive, the little a allele? Okay, let's look at some phrases before we start working problems and just determine what term or what variable each phrase is describing. For example, if I say in a population of 500 individuals, the frequency of the recessive allele is 5%, I'm only talking about one allele, not an allele combination, so I'm strictly talking about Q there, the frequency of the recessive allele. If I was working a problem, I might write down Q equals 0.05. In these problems, I'm going to be working in decimals. Okay, next one. In a population of 1,000 individuals, 250 show the recessive trait. Well, hopefully you remember that the only way to show a recessive trait is if you have an allele combination or a genotype that's homozygous recessive. So this phrase is referring to Q squared. Not just Q. You can't just have a recessive allele. You need an allele combination or a genotype that's homozygous recessive. So if I was working a problem, I would probably start off with Q squared equals 250 over 1,000. Once again, turning it into that decimal of 0.25. Okay, next one's talking about albinism being an autosomal recessive trait. It's telling you the percentage of the population that are albinos. Well, the only way to be an albino is to have a allele combination or a genotype of being homozygous recessive. So once again, this phrase is talking about the term Q squared. In a population of 1,000 individuals, 875 show a dominant phenotype. This one's slightly different. Hopefully you remember that to show a dominant phenotype, you can either be homozygous dominant or heterozygous. So really this information is telling me about two terms put together. You can either be homozygous dominant or heterozygous. So 875 out of 1,000 fall into one of these two variables. I don't know if they're homozygous dominant or heterozygous, but together that gets me my 875 individuals. Okay, the last three on this page are referring to fur color in mice. Brown is going to be dominant over white. The first one says that in a population of 50, 35 are white. Well, think to yourself, okay, what do you need to be white, have white fur color? That's going to be homozygous recessive. So this information is describing the term Q squared. Okay, why Q squared, not Q? Because you need an allele combination to be white. You can't just have one recessive allele. You need to be homozygous recessive to have white fur. Okay, brown fur being dominant over white fur again. The frequency of the big B allele is 0.5. This time it's not talking about allele combination. It's not talking about a genotype. It is strictly telling you about the percentage of the alleles that are dominant. So this one's referring to P. In a problem, I would probably write down P equals 0.5. Last one, 48% of our mice are big B, little b. That's an allele combination. That's a genotype. So that's either going to be P squared, Q squared, or 2PQ. And since it's heterozygous, that's our 2PQ term. Don't forget the 2, include that. Think of that as one variable altogether. 2PQ represents your heterozygous individuals. Okay, so before you start working any Hardy-Weinberg problems, make sure you really understand the difference between the P and Q, representing your dominant or recessive alleles, versus your P squared, Q squared, and 2PQ, representing your three different allele combinations or genotypes in the population. Okay, I guarantee you need to know these variables and those equations before we start working any problems.